Hello everyone, today I have a new video over structures in my YouTube series titled Under the Hood, where I analyze common computer science topics and explain how they really work. So, what are structures? Well, they're user-defined data types in C++ that store a collection of variables, and they're created using the struct keyword. So here we have an example of a structure being created, where we store the name and age of a user, and as an example we create someone named Mark, who is 35 years old. Now, when structures are made, the C compiler essentially assigns a block of memory where each variable or member is located at a specific offset from the start of the block. So, take our friend Mark here, and we'll just take his first initial for simplicity's sake. If we look at the assembly code here, we see that his first initial is located at an offset of -8 from the base pointer, and his age, which is 35, is located at an offset of -4. Now, additionally, recall that the char type is 1 byte and the int type is 4 bytes. But if we look at our table of our data, we can see that we may have some wasted space in the middle here. So you might be wondering why Mark's first initial is not stored in an offset of -5 instead, so we don't have 3 bytes of wasted space. Now, this has something to do with something called structure padding, which is something that compilers do because modern processors are designed around accessing memory in chunks of 4 or 8 bytes. And unaligned data might mean that the processor may need to read in two memory values and then combine their results, leading to reduced performance. So let's have another table here that represents an unpadded structure, or a packed structure as we call them. As we can see, our age value, or 35, is misaligned, meaning the processor may take longer to access it because it spans a memory boundary of 4, which can lead to performance penalties on certain architectures. So here we have some C code where we create two structures, one unpacked and one packed, and we assign some data to them. Now we can use this attribute here to essentially tell the C compiler to pack this structure. Now, if we go ahead and open the assembly output, we can focus on these four lines. And the first two are for the unpacked structure, where we assign the char value at an offset of -8 and the int value at an offset of -4. Now, remember, there are sort of 3 bytes of padding in between the char and the int. Whereas on our packed structure, we can see that they are right next to each other. So there's no padding, so the value of b is assigned right next to the value of 35. You may be wondering then, why pack structures if it leads to such a performance slowdown? Well, there are two main reasons. The first one is to save memory. When dealing with thousands or millions of structures, reducing padding can significantly lower memory usage, which is especially useful in memory-constrained environments. The second reason is to directly map data from a file or network stream into a structure. So take this image, for example. It's stored in the bitmap format. Now, each bitmap has a file header, an information header, and then the actual pixel data. And let's go ahead and take the file header and represent it as a structure. As you can see here, we have each item as a structure member. So when we're working with formats like bitmaps or BMP, packed structures allow us to read the file's binary data directly into memory without manually extracting each field. To show this, let's represent our structure as a table on the left and the image data on the right. As you can see, each value in the image on the right directly follows one another, or essentially has no padding, while the one on the left has padding between the type member and the file size member, because remember, this is a structure in memory. So if we try and copy the entire header from the image to the structure, the type is put in the right place, but when we continue copying the entire header into the structure, the values get misaligned because the compiler has inserted padding. This means the file size member does not land where it should, causing incorrect data interpretation. So the solution is to pack the structure to remove padding and ensure its layout exactly matches the binary file format, so there's no misalignment when reading the data. Now, the final topic we'll go over is something called bitfields, which are used to set a limit on the bits available per member variable. So here we have an example of a structure with a member variable called status and a set bit field of 2. When we try and set a value of 3 to the variable, it works because 3 takes up 2 bits. But if we try and put in 4, it doesn't, as 4 takes up 3 bits, and what happens is up to the compiler you're using. So some will truncate the value, making it 0, while others may issue a warning. Now, when we compile it to assembly, we get this behemoth, so let's go over it line by line. The first line is MOV-ZBL, which is a mnemonic for move 0extend byte to long. So we move the value located at a -4 offset from our base pointer into the EAX register, And on the right, the red bits are the ones that actually represent our value that we have in our structure member variable. The reason we move the value into the EAX register is that we can do more manipulations, and we zero extend it to ensure that only the 8-bit value is preserved in the lower 8 bits of the EAX register, while the upper 24 bits are cleared to 0. The next line is to perform a bitwise OR with the value 3 on the EAX register. In the original code, the status was assigned the value 3, so then performing the OR operation on EAX with 3 will ensure the lower 2 bits are set to 1, which aligns with the logic of initializing status to 3 before we assign it 4 later. After that, we move the value in the AL register, which is the lowest byte of the RAX, EAX, AX register, back into the original spot, which is at an offset of -4 from our base pointer. Only the lowest byte of EAX stored in AL is moved back into memory. Now, when moving the value of 4 into our member variable, the first and last line look identical, which is moving the value in and out of the EAX register. However, the middle line performs a bitwise AND operation with 4, which sets the value in the EAX register to 0. This makes sense as when the GCC compiler, which is what this program is currently using, encounters a value with more bits than the specified bit field size, it will truncate the value, in this case to 0. Now, the reason we use bitfields is often to store data flags, such as a flag for a player in a video game that represents whether they are hungry or sleepy or still alive. And with that, when it comes to structures, that's a wrap. Thank you for watching, and I look forward to seeing you in the next video.